sklearn inspection. Description: sklearn inspection refers to the process of examining and understanding the behavior and performance of a trained machine learning model built using scikit-learn sklearn library in Python. This involves analyzing various aspects of the model, such as its internal structure, feature importance, prediction accuracy, and potential biases. Inputs: trained sklearn model. The trained machine learning model, which is an object containing the learned parameters and decision boundaries based on the training. Data: feature data. The dataset containing the features used for training and testing the model. It can be a pandas data frame or a NumPy array. Target data: the labels or target values corresponding to the feature data. Outputs: model performance metrics, evaluation metrics like accuracy, precision, recall, F1 score, AUC, etc. to assess the model's predictive capabilities on the test data. Feature importance: information on the relative importance of different input features in influencing the model's predictions. Model parameters: the values of parameters used during model training, which can be adjusted for fine-tuning. Visualization plots: graphical representations of the model's behavior and performance, such as confusion matrices, ROC curves, feature importance plots, and decision boundaries. Model explanation: insights into how the model makes predictions, often through techniques like partial dependence plots, SHAP values, or LIME explanations. Steps: model evaluation: evaluating the trained model's performance on a separate test dataset using relevant metrics. Feature importance analysis: identifying which features contribute the most to the model's predictions. Model visualization: creating plots to understand the model's behavior, feature interactions, and decision boundaries. Parameter inspection: examining the values of parameters used during training to understand their impact on the model's performance. Model explanation: generating insights into the model's decision-making process to enhance interpretability and trust. Metrics: accuracy: proportion of correct predictions made by the model. Precision: ratio of correctly predicted positive cases to all predicted positive cases. Recall: proportion of correctly predicted positive cases to all actual positive cases. F1 score: harmonic mean of precision and recall. AUC: area under the curve, area under the receiver operating characteristic, ROC curve. Measuring the model's ability to discriminate between classes. Mean squared error: MSE measures the average squared difference between predicted and actual values for regression tasks. Visualization plots. Confusion matrix: a matrix that summarizes the performance of a classification model by showing the counts of true positive, true negative, false positive, and false negative predictions. ROC curve: a graphical plot that shows the relationship between the true positive rate and false positive rate for different classification thresholds. Feature importance plot: a bar chart or heat map that displays the relative importance of each feature in contributing to the model's predictions. Partial dependence plot (PDP): a plot that shows the marginal effect of a feature on the model's predictions, keeping other features constant. Decision boundary plot: a visualization of the decision surface that separates different classes in a classification model. Fine-tune parameters: regularization parameters used to prevent overfitting, such as L1 lasso and L2 ridge regularization. Learning rate controls the step size during model optimization. Number of estimators for ensemble models: the number of individual models combined in an ensemble. Maximum depth for tree-based models: the maximum depth of individual decision trees in the ensemble. Uncertainty methods: Confidence intervals measures of the uncertainty around the model's predictions, typically calculated using bootstrapping or other resampling techniques. Prediction intervals ranges of values within which the model's predictions are expected to fall with a certain probability. Bayesian inference, a framework that provides a probabilistic interpretation of the models. Parameters and predictions. Challenges and fixes. Challenge 1: overfitting. The model performs well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: a model trained on a limited dataset with complex features might learn patterns specific to the training data, leading to overfitting. Fixes to challenge 1. Use regularization techniques L1, L2 to penalize complex models. Increase the size of the training data. Use cross-validation to assess model performance on different subsets of the data. Employ early stopping to prevent overtraining. Challenge 2: underfitting. The model fails to learn the underlying patterns in the data, leading to poor performance on both training and testing data. Sample use case that resulted in challenge 2: a model with a simple architecture might be unable to capture complex relationships in the data. Fixes to challenge 2. Increase the complexity of the model by adding more layers or features. Optimize model hyperparameters, such as learning rate and regularization parameters. Try different model architectures to find one that is more suitable for the data. Consider using feature engineering to create new features that are more informative. Challenge 3: high variance. The model's predictions are sensitive to small changes in the training data, leading to inconsistent performance. Sample use case that resulted in challenge 3: a model with a large number of features or a complex structure might be prone to high variance. Fixes to challenge 3. Use regularization techniques to reduce the model's complexity. Increase the size of the training data to improve generalization. Employ ensemble methods, such as bagging or boosting, to combine multiple models and reduce variance. Challenge 4: high bias. The model is too simple and fails to capture the true relationships in the data, leading to consistent but inaccurate predictions. Sample use case that resulted in challenge 4: a linear model might not be able to capture nonlinear relationships in the data. Fixes to challenge 4. Use more complex model architectures, such as nonlinear models, e.g., decision trees, neural networks. Add more features to the model. Use feature engineering to create more informative features. Challenge 5: data imbalance. The dataset contains an unequal distribution of classes, which can bias the model towards the majority class. Sample use case that resulted in challenge 5: a classification model trained on a dataset with many more examples of one class than another might favor that class during prediction. Fixes to challenge 5. Use oversampling techniques to increase the number of samples from the minority class. Use undersampling techniques to reduce the number of samples from the majority class. Employ cost-sensitive learning, where the model assigns higher penalties to misclassifications of minority class instances. Challenge 6: missing data. The dataset contains missing values, which can affect the model's training and performance. Sample use case that resulted in challenge 6: a model might not be able to handle missing values properly, leading to inaccurate predictions. Fixes to challenge 6. Impute missing values using techniques like mean imputation, median imputation, or more sophisticated methods like KNN imputation. Use models that can handle missing data, such as decision trees or some neural network architectures. Design features that are robust to missing values. Challenge 7: data leakage. Information from the test data is unintentionally used during training. leading to overly optimistic performance evaluations. Sample use case that resulted in Challenge 7 using features derived from the target variable during training can lead to data leakage. Fixes to Challenge 7. Carefully examine the features used for training and ensure that they do not include information from the test data. Use proper data splitting techniques to prevent leakage during cross-validation or model evaluation. Employ techniques like holdout validation or time series cross-validation to avoid leakage in time-dependent data. Challenge 8 Interpretability. The model's predictions are difficult to understand and explain, making it challenging to trust or deploy. Sample use case that resulted in Challenge 8 black box models, like deep neural networks, can be complex and difficult to interpret. Fixes to Challenge 8. Use techniques like partial dependence plots, SHAP values, or LIME explanations to generate insights into the model's predictions. Choose more interpretable model architectures, such as decision trees or linear models. Implement techniques to simplify or visualize the model's decision boundaries. sklearn inspection partial dependence. Description partial dependence plots PDP help visualize the marginal effect of a feature on the target variable, keeping all other features constant. It provides insights into how a specific feature influences the prediction. Inputs: model a trained machine learning model, e.g., decision tree, random forest, neural network. Feature: the specific feature you want to analyze. Data: the dataset used for training the model or a subset. Outputs: PDP plot a visual representation of the feature's impact on the target variable, typically showing the average predicted value across different feature values. Feature values: the range of values of the selected feature used for plotting the PDP. Steps: feature selection: specify the feature you want to analyze. Grid creation: create a grid of values for the selected feature. Prediction: for each value in the grid. Predict the target variable for each observation in the data, while keeping all other features constant. Average prediction: calculate the average predicted value for each feature value in the grid. Visualization: plot the average predicted values against the corresponding feature values to create the PDP. Metrics: non-PDPs do not directly measure a specific metric, but they visually depict the relationship between a feature and the prediction. Visualization plots: PDP plot a line plot showing the average predicted value against the corresponding feature values. This plot helps visualize the effect of the feature on the target variable. ICE plots: individual conditional expectation plots show the predicted value for each individual observation as the selected feature changes, providing more granular information than the average PDP. Fine-tune parameters: grid size: the number of values in the grid for the feature. A finer grid can provide more detailed information, but may require more computational time. Feature values: you can specify a custom range of values for the feature instead of using the entire range from the data. Percentiles: specify percentiles to determine the feature value range used for the PDP. Uncertainty methods: non-PDP itself doesn't provide uncertainty estimates directly. However, you can use techniques like bootstrapping or permutation tests to quantify the uncertainty in the PDP estimates. Challenges and fixes. Challenge 1: high-dimensional datasets. In datasets with many features, PDPs can become difficult to interpret. as the marginal effect of one feature might be influenced by interactions with other features. Sample use case: a model predicting house prices with 20 features, where the PDP for number of bedrooms might be confounded by interactions with location or square footage. Fixes: feature selection: prioritize analyzing PDPs for features that are deemed important based on feature importance scores or domain knowledge. Partial dependence: with interactions, use techniques like the individual conditional expectation, ICE plots, or generalized additive models (GAMS) to explore the interactions between features. Challenge 2: nonlinear relationships. PDPs might not accurately represent complex nonlinear relationships between the feature and the target variable. Sample use case: a model predicting customer churn where the relationship between age and churn might have an S-shaped pattern not easily captured by a linear PDP. Fixes: nonlinear models. Consider using models that can capture nonlinear relationships, e.g., decision trees. Support vector machines with nonlinear kernels. Advanced PDP methods explore methods like Friedman's edge statistic for a more nuanced analysis of the interaction between features. Challenge 3: high cardinality categorical features. PDPs can become difficult to interpret for categorical features with a large number of distinct values. Sample use case: a model predicting product sales with a category feature that has hundreds of different product categories. Fixes: feature engineering. Consider transforming high cardinality categorical features into lower dimensional representations, e.g., using one-hot encoding, hashing, or embedding techniques. Grouping categories: group similar categories together to reduce the number of distinct values for easier analysis. Partial dependence plots with binned features: use methods to analyze PDPs for features that have been binned into categories. sklearn inspection permutation importance. Description: explain in detail. Permutation importance is a technique used to assess the relative importance of features in a machine learning model by measuring how much the model's performance decreases when a specific feature is randomly shuffled or permuted. This method provides insights into which features contribute most significantly to the model's predictions. Inputs. Input 1: explain in detail. Estimator: a trained machine learning model. This could be a classification or regression model, such as a random forest, logistic regression, or support vector machine. Input 2: explain in detail X, the dataset containing the features. Input 3: explain in detail Y, the target variable or labels. Input 4: explain in detail scoring, the scoring function used to evaluate the model's performance. Examples include accuracy, precision, recall, F1 score, mean squared error, etc. Input 5: explain in detail N repeats, the number of times the permutation process is repeated for each feature to obtain more robust results and estimate uncertainty. Input 6: explain in detail N jobs, the number of CPU cores to use for parallel processing, which can accelerate the permutation process. Input 7: explain in detail random state, a seed value for the random number generator used during permutation. Input 8: explain in detail refit, a Boolean flag indicating whether to refit the model on the permuted data. This can be helpful for complex models where refitting may be necessary for accurate performance. Evaluation. Outputs. Output 1: explain in detail importance, a pandas data frame containing the permutation importance scores for each feature. The scores indicate how much the model's performance drops when the feature is shuffled, providing a measure of its importance. Output 2. Explain in detail results. A dictionary containing the detailed results of a permutation importance analysis for each feature. The dictionary includes the feature name, the mean importance score, the standard deviation of the scores, and the raw scores from each permutation. Steps. Step 1. Explain in detail shuffle feature for each feature. The values are randomly shuffled or permuted while keeping other features unchanged. Step 2. Explain in detail evaluate model. The model is evaluated using the scoring function on a dataset with the permuted feature. Step 3. Explain in detail calculate importance. The difference between the model's performance on a original data and the permuted data is calculated. This difference represents the importance of the permuted feature. Step 4. Explain in detail repeat process. Steps 1 to 3 are repeated multiple times for each feature to estimate the importance score and its variability. Metrics. Metric 1. Explain in detail mean importance, the average importance score across multiple permutations. Metric 2. Explain in detail standard deviation of importance, a measure of the variability of a importance scores, indicating the uncertainty in the estimation. Visualization plots. Visualization plot 1. Explain in detail bar plot. A bar plot can be created to visualize the feature importance scores, allowing for easy comparison of the relative importance of different features. Visualization plot 2. Explain in detail box plot. A box plot can be used to illustrate the distribution of importance scores for each feature, providing insights into the variability and uncertainty. Fine-tune parameters. Parameter 1. Explain in detail n repeats. Increasing the number of repetitions n repeats can provide more robust and stable importance scores, particularly for complex models or when there is high noise in the data. Parameter 2. Explain in detail scoring. Selecting an appropriate scoring metric. Scoring is crucial for interpreting the results correctly. Uncertainty methods. Uncertainty method 1. Explain in detail standard deviation of importance. The standard deviation of the importance scores, calculated across multiple permutations, provides a measure of the uncertainty in the estimation of importance for each feature. Challenges and fixes. Challenge 1. Explain in detail high feature correlation. If features are highly correlated, permutation importance may not accurately reflect their individual contributions. The model may be using a combination of correlated features, and shuffling one feature may not have a significant impact on performance. Sample use case that resulted in challenge 1. A model predicting house prices may have highly correlated features like square footage and number of bedrooms. Fixes to challenge 1. Feature selection. Consider using feature selection methods, e.g., recursive feature elimination, to identify and remove redundant features before using permutation. Importance. Regularization techniques. Techniques like L1 regularization lasso can help to penalize models with many features, potentially reducing the impact of correlated features. Feature engineering. Combine highly correlated features into a single feature that captures their joint effect. Challenge 2. Explain in detail nonlinear relationships. Permutation importance may underestimate the importance of features involved in complex nonlinear relationships with the target variable. Sample use case that resulted in challenge 2. A model predicting customer churn may have a nonlinear relationship between customer tenure and churn probability. Fixes to challenge 2. Feature engineering. Create new features that capture nonlinear relationships. For instance, consider adding polynomial terms or interaction terms between features. Model selection. Choose models capable of capturing nonlinear relationships, such as random forests, gradient boosting machines, or neural networks. Use of Shapley values. Explore alternative methods like Shapley values, which are more sensitive to nonlinear interactions and provide a more accurate assessment of individual feature importance. sklearn inspection decision boundary display. Description. Explain in detail the decision boundary display class in scikit-learn is a visualization tool used to represent the decision boundary of a classifier on a 2D feature space. It helps to understand how a classifier separates different classes based on the input features. Inputs. Input 1. Explain in detail classifier. This is the trained classifier model from scikit-learn that you want to visualize the decision boundary for. The classifier should be a binary or multi-class classifier. Input 2. Explain in detail X. This is the 2D feature array containing the data points used to train the classifier. It should have 2 features columns for the visualization. Input 3. Explain in detail Y. This is the target array containing the labels for the data points in X. The labels should be compatible with the classifier's output. Outputs. Output 1. Explain in detail a matplotlib access object containing the visualization of the decision boundary. This object can be further customized using matplotlib methods. Steps. Step 1. Explain in detail the decision boundary display. From estimator method is used to create an instance of the decision boundary display class. Step 2. Explain in detail the plot method is called on the decision boundary display object to generate the visualization. Step 3. Explain in detail the ax attribute of the decision boundary display object allows you to access the matplotlib access object for further customization. Metrics. Metric 1. Explain in detail the decision boundary display class itself does not directly provide metrics. However, the underlying classifier that it visualizes can be evaluated using metrics such as accuracy, precision, recall, F1 score, and AUC. Visualization plots. Visualization plot 1. Explain in detail the plot generated by decision boundary display shows the decision boundary of the classifier as a line or curve that separates the different classes in the feature space. Visualization plot 2. Explain in detail the data points from X are also plotted on the same axes, colored according to their labels in Y. This allows you to see how well the decision boundary separates the classes. Fine-tune parameters. Parameter 1. Explain in detail plot method. This parameter determines the method used to plot the decision boundary. It can be either contour or decision function. Contour will generate a contour plot representing the decision boundary, while decision function will use the decision function of the classifier to directly plot the boundary. Parameter 2. Explain in detail CMAP. This parameter specifies the color map used for plotting the data points. This parameter accepts a matplotlib color map. Parameter 3. Explain in detail alpha. This parameter controls the transparency of the data points. Values range from 0 completely transparent to 1 completely opaque. Parameter 4. Explain in detail X label. This parameter allows you to set the label for the X-axis of the plot. Parameter 5. Explain in detail Y label. This parameter allows you to set the label for the Y-axis of the plot. Parameter 6. Explain in detail title. This parameter allows you to set the title of the plot. Parameter 7. Explain in detail plot decision boundary. This parameter controls whether to plot the decision boundary. By default, it is set to true. Parameter 8. Explain in detail. Plot data points. This parameter controls whether to plot the data points from X. By default, it is set to true. Uncertainty methods. Uncertainty method 1. Explain in detail. The decision boundary display class itself does not directly provide uncertainty visualization. To visualize uncertainty, you can utilize the capabilities of the underlying classifier or use techniques like confidence intervals or prediction probabilities. Challenges and fixes. Challenge 1. Explain in detail incorrect feature scaling. If the features in X have significantly different scales, the decision boundary might be skewed, making it difficult to interpret. Sample use case that resulted in challenge 1. You are trying to visualize the decision boundary of a classifier trained on data with features such as age ranging from 18 to 80 and income ranging from 10,000 to 1 million. The different scales of these features might lead to an unevenly stretched decision boundary. Fixes to challenge 1. Apply feature scaling techniques like standardization or normalization before using the decision boundary display class to ensure that the features have similar scales. Challenge 2. Explain in detail overfitting. If the classifier is overfitting to the training data, the decision boundary might be very complex and might not generalize well to unseen data. Sample use case that resulted in challenge 2. You are using a complex classifier with a large number of parameters, and it has achieved very high accuracy on the training set. However, it performs poorly on the test set, indicating overfitting. Fixes to challenge 2. Use techniques like regularization or cross-validation to prevent overfitting and improve the generalization of the classifier. Challenge 3. Explain in detail high-dimensional data. The decision boundary display class is designed for visualizing classifiers with two features. For higher dimensional data, it is not possible to visualize the decision boundary directly. Sample use case that resulted in challenge 3. You have a data set with 10 features. You want to visualize the decision boundary of a classifier trained on this data. Fixes to challenge 3. You can either select two features that are most relevant to the classifier's decision making and visualize the decision boundary in that 2D subspace, or use dimensionality reduction techniques like PCA to reduce the dimensionality of the data before visualizing a decision boundary. Challenge 4. Explain in detail nonlinear decision boundaries. Decision boundary display might not be able to perfectly represent nonlinear decision boundaries, especially if the decision boundary is highly complex. Sample use case that resulted in challenge 4. You are using a nonlinear classifier like a support vector machine with a nonlinear kernel, and the decision boundary is a curved line or a complex shape. Fixes to challenge 4. The decision boundary display can still be used to visualize the general shape of the decision boundary. However, for more accurate representation of nonlinear boundaries, you may need to explore other visualization techniques or consider using specialized libraries for visualization. sklearn inspection. Partial dependence display. Description. Partial dependence display (PDP) is a model inspection technique that visualizes the marginal effect of a single feature or a pair of features on the predicted outcome of a machine learning model. It helps to understand how changes in the selected feature influence the model's predictions, while keeping other features constant at their average values. Estimator. The fitted machine learning model. It could be any model that has a predict method, e.g., linear regression, random forest classifier, etc. X. The feature matrix used to train the model. It should have the same format as the data used for training. Features. A single feature name or a list of feature names to analyze. If a list is provided, It creates a 2D PDP for the interaction of those features. Kind the type of PDP plot to create. Average shows the average predicted value for each feature value. Individual shows the predicted value for each individual data point. Subsample the number of data points to use for calculating the PDP. It can be a fraction or an integer. Smaller values can speed up computation but may lead to less accurate plots. Grid resolution: the number of grid points to use for each feature when calculating the PDP. Higher values result in smoother plots but may increase computation time. Centered: whether to center the PDP plot around the average predicted value. This can help to visualize the effect of the feature more clearly. N jobs: the number of CPU cores to use for parallel computation. Higher values can speed up calculation, especially for large datasets. Random state: the random seed to use for shuffling data if subsampling is used. Ensures reproducibility of the plot. Display: a partial dependence display object. It stores the plot data and provides methods for customizing and displaying the plot. 1. Feature selection: specify the feature or pair of features you want to analyze. The PDP will visualize the effect of this feature on the predicted output. 2. Data subsampling: if necessary, subsample the data to reduce computation time. This is especially helpful for large datasets. 3. Grid creation: create a grid of feature values for the selected feature or features. The PDP will show the model's prediction for each grid point. 4. Prediction calculation: for each grid point, make predictions with the trained model. Keep other features constant at their average values. 5. Plot creation: visualize the relationship between the feature values and the predicted outputs. This is often done using a line plot or a heat map. No direct metrics associated with PDP itself. It's a visualization technique for understanding model behavior, not for calculating performance metrics. Line plot: commonly used for single feature PDPs. The x-axis represents the feature values, and the y-axis represents the average predicted value. Heat map: used for two feature PDPs. The x and y axes represent the values of the two features, and the color intensity represents the average predicted value. Grid resolution: adjust the number of grid points to create smoother plots or reduce computation time. Subsample: modify the number of data points used for PDP calculation to balance speed and accuracy. Kind: choose between average and individual plots to visualize the average or individual predictions. Confidence intervals can be added to PDP plots to show the uncertainty in the estimated effect of the feature. This gives a better understanding of the reliability of the results. Challenge 1: high computation time calculating PDP for many features or with high grid resolution can be computationally expensive, especially for large datasets. Sample use case that resulted in challenge 1: working with a dataset of millions of data points and 100 features. Calculating PDP for all features resulted in a lengthy computation time. Fixes to challenge 1: reduce the number of features analyzed. Prioritize features that are most relevant to your analysis. Decrease grid resolution. This may lead to less smooth plots but can significantly reduce computation time. Utilize subsampling. Select a representative subset of the data to calculate PDP. Employ parallel processing. Use N jobs to leverage multiple CPU cores for faster calculations. Challenge 2: misleading results. PDP can be misleading if there are complex interactions between features or if the model is highly nonlinear. Sample use case that resulted in challenge 2: a model with strong interactions between two features. might show incorrect interpretations when using single feature PDPs. Fixes to challenge to use two feature PDPs. Visualize the interaction between relevant features to capture the true effect. Consider other model inspection techniques. Explore methods like partial dependence plots with interactions, permutation importance, or SHAP values to gain deeper insights.